Dr. Huckabee here again. Another lecture on Chapter 6, this time on kinetics and starting into a little bit about nucleophile, electrophile identification. I hope you enjoy it. Here is your to-do list. Do your homework assignment, finish reading Chapter 6, and work as many Chapter 6 problems as you can. Pretty short and simple. Good luck.
But what about if I told you that it's not always that easy? So let's say you have your reactants. We'll just keep them R. And let's say you make either A or B. You can draw, and I told you that the reaction diagrams for them look like this. Could you tell me which reaction is more thermodynamically favored? We're taking a small skip and a jump to a concept here. Remember what thermodynamics are. They are what? They are enthalpy and they are entropy. We're talking about free energy change. Which one, A or B, is thermodynamically favored? Raise your hand if you think it's A. Raise your hand if you think it's B. Look at you guys. So happy. Yeah, it's B. Good job. Which one of these is kinetically favored? What do you think I mean when I say kinetically favored? It has to be a difference in energy also, right? What energy have we been talking about? Yeah, activation energy. Exactly. So which one of these is kinetically favored then? Raise your hand if you think it's A. If you think it's B. All right. Okay, a lot more abstentions that time. Kinetics is about the rate. Okay? Always remember that. Kinetics is about rates. In reaction diagrams, you express a rate using the activation energy. So we'll say that, the little one goes with B, and the big one goes with A. Hopefully you can see from this very crude drawing that B, the activation energy for B, ooh, I'm getting swirly there today. The activation energy for B is a lot less than it is for A, right? But, because this is a fun game, what if I told you that that wasn't always going to be the case? What if I told you that sometimes you can have reaction diagrams where you have a reactant, and you have A and B, but now the actual curves look something like this. So now I got to ask, which product is thermodynamically favored? Take a second, have a look. Remember what thermodynamics are. Raise your hand if you think it is A. Okay, thermodynamically favored A. Raise your hand if you think it's B. What is thermodynamic, or how do we gauge if something is favored thermodynamically? Free energy change. I think I heard it. So which one of these is farthest away from this line, has more distance in the negative direction? It's B. B has a higher change in free energy that is negative. It is thermodynamically favored. Which one is kinetically favored? Who here thinks it's B? Who here thinks it's A? A, okay, good. A is kinetically favored because the activation energy is smaller. right? Way smaller than it is for B. Does that make sense to you guys? So now let me ask you one last question. Say I gave you whatever R was in a bottle, and I told you I want you to make me only A. A and B are both possible, but what would you do in a lab to get me only A? It's no big deal if you don't, but I will fire you. Remember, kinetics is about rate, and there are really three things that we talked about that really influence the rate of a reaction. First was the activation energy, and we already saw that there's a big difference there between the two. We can't really change that, right? Second was temperature, and third was sterics. We don't really know what molecule we're talking about here, so sterics is probably not the right answer. Temperature can be the biggest difference in thermodynamics because, in controlling what a reaction does. And the reason for that, I'll go right back to our really fun warped wall question. Oops. The reason for that is that as you increase the temperature, you start to move that green bar up closer and closer and closer to the activation energy, which means even if you have a big difference in the activation energy of 2, you'll be able to get some molecules up here. And here's a thing I haven't told you yet because it hasn't been important until this moment. Every reaction we've talked about so far in energetics here is not one way. Right? This is what you're thinking I'm asking you, right? R goes to A or B. However, it's actually, do this in red. It's actually R goes to A or B and can be brought back. Because if you just flip this around, now you can have A or B going to R with the same activation energy barrier, right? Therefore, as you increase the temperature, let's say, let me redraw this. So we'll draw another guy here. Oh, that's not what I want. There we go. Draw that. In our reaction progress. So remember always E is increasing and reaction progress is always advancing. So now if we have R going to A and B, here's R, A and B, we know that we have two different activation energies. I'm going to make B red again, and I'll leave A blue. Okay, so let me put this to you a different way, because it's something that is very, very useful, and then we'll talk about a lot, is kinetic versus thermodynamic control. If I told you we only had enough energy, or that the temperature left the energy of the molecules here, roughly, which of these two reactions would you say is the most probable to occur? It would be the one with the smaller activation energy, right? Because there's less energy for the molecules to actually do the reaction, so the smaller activation energy should be preferred. Therefore, you could be pretty certain that A was going to happen at low temperature. Because low temperature means what? Low energy. However, at high temperature, the energy is increased, right? You're adding so much energy there into the reaction. So let's say that's where your energy is. So now every molecule is free to go one way and back the other way in an equilibrium. Therefore, if they're free to go back and forth as they please, and there's no barrier to activation there, the thermodynamically favored molecule will always be the one that's left in highest quantities. Because, just like when you burn paper or when you make beer from sugar, you are going to the lowest energy. Because that's the second law of thermodynamics, right? You're trying to reduce as much energy as possible. And so if you have a very high temperature, your equilibrium will settle around the one with the lower Gibbs free energy. And if you have a lot lower temperature, the blue one, then even if you make A, and it's in an equilibrium, and the molecule can go back over this barrier, there's no way it can get up and go back to R and reconvert to B. There's no way. So they would be stuck here in A and would never have enough energy to get over the hump there. Does that make sense? I hope it does, because there are many reactions you'll learn where you can have one thing happen or another depending on how much energy is available in the system. And it's really good if you can remember that one of these things is kinetically controlled and the other one is thermodynamically controlled. Right, so moving on from talking about the control of a reaction, I want to go back to thinking about this reaction diagram because I mentioned that 2 and 4 were the same thing and that they are transition states. But I didn't tell you what they were because I wanted to go on that rant about kinetics and thermodynamics. Transition states essentially are the point that a reaction must go through between reactants and products. Otherwise, the reaction won't happen. And what this means is, let's say you have a reaction like let's say you have a very simple nucleophilic substitution reaction, which you'll learn about, don't worry, which is this methyl bromide being attacked by iodide, leaving you with methyl iodide and a bromide anion. Let's just say you don't have to worry about what this reaction really is. What you really need to know is that a transition state for this reaction would have a structure that kind of looks like this, where on one side you have the bromine, and this bond is about to be broken because we're at the highest energy for our reaction. And on the other side, you have the iodine, or the iodide, and that bond is just about to be formed. Like they're close enough to where there's an interaction, but it isn't formed just quite yet. And this is a real structure that must exist because otherwise this reaction wouldn't take place. Now that being said, it must exist, but you cannot detect it by definition. Because imagine that the top of the transition state is like the most severe precipice you can imagine. And you cannot stand on top of this precipice, or sorry, this pinnacle, without falling off. And that's exactly what a transition state is. As soon as you reach it, you immediately go to products. Or as soon as you reach it, you immediately go back to reactants. And we call this transition state, we bracket it typically, and we'll put on this double dagger. And often you'll see it written like TS double dagger or something, especially in biochemistry. They'll use double dagger for a lot of things. And the really cool thing about transition states is that, one, they exist, and that's already cool. Two, there's this really great theory on transition states that talk about exactly what they look like. Okay. So I'll just leave this there while I sort out my life. There we are. Okay, so that was 4, so we're on 5 now. So there's this great theory from a chemist named Hammond, that is the Hammond postulate. And essentially what Hammond said, what Hammond said was that if you have a reaction diagram where you have reactants going to products, depending on if the reaction was exothermic or endothermic, the transition state would look more like the reactants or the products. So let's start with the exothermic version. Right? Okay. Identify the transition state, which is here. What Hammond says is that because you're putting in energy from the reactants, and the reactants are closer to energy, closer in energy to the transition state than are the products, the transition state will look more like the reactants. The converse is also true. If you have a different reaction, again, energy is always increasing going up, and the reaction is progressing going to the right, and you have reactants going to products. Oh, that's the same thing. This. And it's endothermic. Transition state is here. And the energy of the transition state is a lot closer to the energy of the products, so the transition state will look more like the products. Again, it's going to be super useful to have this knowledge later, but for now, as is often the case in organic chemistry, I have to give you the very vague, most broad definitions of things because it's like a foreign language, and later we'll learn how to apply those very broad ideas in reactions. It's a lot like when you learn verbs. You learn verbs, and then later you learn how to conjugate them in Latin languages, for instance. Ooh, it must be 6. Okay, we are almost there. Oh, double. Yeah, that's pretty much all we need to know right now for the Hammond postulate. We will definitely come back to it, though. So, before we can move into Chapter 7 and really, get to real organic chemistry reactions, we need to learn a couple of things. First, we need to learn how to identify nucleophiles and electrophiles. And we need to learn how to push arrows to make mechanisms. First, let's go over the nucleophiles and electrophiles. Okay, so nucleophiles, they're electron-rich. Electron-rich atoms that are attracted to partially or fully positive atoms. And because of this electrostatic attraction, they react. Electrophiles are kind of like the exact opposite. They are either fully or partially positively charged, and they react with a nucleophile by accepting electron density. So nucleophiles give electron density, and electrophiles accept electron density. It's a lot like Lewis acids and Lewis bases. So we could draw some very simple reactions incorporating nucleophiles and electrophiles. There we are. So this would be a basic nucleophilic attack on this tertiary carbocation. If you remember, maybe if you don't remember, carbocation, as I have drawn here, is just a fully positive charge on a carbon, a cation. So we call it a carbocation. And this reaction happens just like that. So what I've drawn is a fully negative molecule with a lone pair attacking a fully positive carbocation atom, but it doesn't always have to happen that way because there are lots of different types of nucleophiles we can have. Sorry, let's get these pictures out of the way. Oh no. Figure it out later. There are lots of types of nucleophiles we can have. So we can have, like what we just saw, we can have a negatively charged molecule. That can be a nucleophile because it has so much electron density around the oxygen. Either of these lone pairs can attack something if it has a partial positive charge, but they don't have to be negatively charged. The lone pairs on this neutral oxygen can also can also attack something, and that would still make the oxygen a nucleophile. Weirdly, we can have another type of nucleophile, and that is a pi bond. Because if you remember, a pi bond has this extra double bond here, and that can actually do the same type of nucleophilic chemistry as can the lone pairs. I'm just not getting this microphone, or I'm moving my head too much. So each of these nucleophiles is actually much different strengths. Typically, if you have a negatively charged nucleophile, it's going to be a lot stronger than a neutral one. And just like any electronegative atom is going to be a lot stronger than is some pi bond. So you could typically say that strength increases in these three going right to left. And the opposite of a nucleophile is an electrophile. And these things can either have fully positive charges, like I drew before with the carbocation, or they can have partially positive atoms, such as this one. And if you remember, there's a dipole. That means the chlorine is partially negative, and the carbon is partially positive. That partially positive carbon will react with a nucleophilic molecule because it is an electrophile. And now that we know what nucleophiles and electrophiles are, we can start to identify the four types of reactions, the basic reaction mechanisms that, like all of organic chemistry, is guided by. There are only four, and if you know these four, you'll probably get any polar type of reaction with a nucleophile and electrophile correct. Of course, you put them together in all different ways, but that's what you'll learn. And to do that, what you really need to do is have a mastery of arrow pushing. And maybe you remember something about arrow pushing because I went on a rant about it earlier in the semester. And also, we've had some experience. Because maybe you remember, test 1 had this question. Where I was asking you to make a resonance structure, right? And you could choose like any structure you wanted. One very popular one oops, was it this guy? And to get to that resonance structure, I asked, I believe, or maybe I didn't ask him the question, I don't remember. But a lot of you drew the arrows in to have the lone pair come down, this pi bond move, and these electrons go up to the oxygen to make this doubly charged resonance form. That is arrow pushing, if you remember. But that wasn't the only place we had arrow pushing. We actually also did arrow pushing in Chapter 3 in the acid-base section because we had some very simple reactions that looked like this. Ooh. Hopefully you guys remember that. And we talked a little bit about how bases physically take the proton from the acid. And those reactions had arrow pushing as well. One for the base to attack the proton, and the second for the arrow or for the electrons to return back to the oxygen. And we had the opposite reactions happening on the other side to regenerate our reactants. So we've done some of this, and you guys have already shown me that you're capable of doing arrow pushing. But now we're going to do it in very different ways. Well, okay, this is actually one type of arrow pushing, but there are some that you haven't seen before and might seem a little weird. The first thing that we're going to do is talk about nucleophilic attack. That is the most basic polar reaction mechanism that can happen in organic chemistry. And nucleophilic attack can either use like one arrow, so if you had, say, bromine that was negatively charged, so it was a bromide, and you added it to this carbocation, you could draw an arrow showing that nucleophilic attack happens from the bromine onto that carbocation, leaving you with this product. But as happened with the reaction diagrams, they won't always be that simple, and you can use more than one arrow at a time. So take this one for instance. Where you have a negatively charged nitrogen, and it's going to attack this molecule. So remember that nucleophiles have to attack something, and they're electrophiles, which have to be partially positively charged. That's going to be here, and you can draw them like this. You can draw that attack happening this way. Second arrow, it's fine. And that's the basics of nucleophilic attack for today. But I do have one very important question for all of you. Can you take this information, directly apply it, and really fast find for me the nucleophile in this next thing I'm going to show you? Okay, remember what a nucleophile is, right? It's the thing that attacks something. So where's the nucleophile in this reaction?